Today's focus will be on the variables of sound. So sound has a few different properties. First off, I want you to know that how do we measure sound or how do we see sound? Okay, because sound travels in a longitudinal sound wave. So we would just see things like this if we were to ever see it. But what we do is we have a machine called an oscilloscope that actually translates this into the transverse wave that we are used to seeing with sound. And you'll see, like, when you look at something screens, it'll be like right, or it'll like, you'll see the different sounds. We don't see lines as you would in a longitudinal. We see the transverse waves. All right. So how can you change sound? If you translate it into a transverse wave, how can we change it? Well, one way is that you're going to change its pitch. What is pitch directly related to? It's directly related to the frequency. So if I want to change my pitch, I just change my frequency. So a low pitch has a long wavelength or a low frequency, and a high pitch has a high frequency or short wavelength. So pitch is due to frequency, but you can also obviously change its wavelength because those are inversely related, right? So if I change one, then I'm changing the other. All right, so once again, oscilloscope is the machine that translates the longitudinal wave into a transverse wave that we see through a machine. And then pitch, how do I change pitch? I change its frequency. How do I change something's volume? Okay, because obviously there's louder and softer sounds, right? And the way that you do that is you change its amplitude. So what is amplitude? Remember, amplitude, if we look at a transverse wave, is from the origin to the crest or from the origin to the trough. So if I want to increase my volume, all I have to do is I have to increase my amplitude. So now it would be louder. This would be louder. Okay, but notice that my frequency is the same, so the pitch would be the same. Okay, but it would just be louder. Also, one way you can remember it is an amplifier. If you ever have some amplifiers, what does it do? It changes the loudness of it. So what are you doing? You're changing the amplitude. So notice that those go together. Okay, and it can increase. All you're doing is basically adding energy to it. So you're adding energy to make these troughs and crests higher. And what do we measure it in? We measure it in decibels. And decibels are a little goofy. Okay, and which we'll get into in a minute. Okay, so let's draw a low pitch wave versus a high pitch wave. Remember, it's a comparison. So a low pitch wave would have a long wavelength. A high pitch wave would have a short wavelength, meaning a high frequency. So you'd have a long wavelength, low frequency, short wavelength, high frequency. Okay, volume, all I have to do is I have to change my height, okay, or my amplitude. So low volume would have a low height or amplitude, and a high volume would have a high amplitude. So as I said, how do we measure volume? We measure it in decibels, okay? And decibels are a little goofy. First off, it's abbreviated as D and then capital B. But it is based off of a tenfold type of change. So if I have 10 decibels, it is 10 times louder than a 0 decibel. You're like, oh, okay, that makes sense. But 20 decibels is not, actually, I shouldn't be, is not 20 times louder than 0. It is actually 100 times. 30 decibels is 1,000 times louder than 0. Okay, so let's try to go how we're doing this. All you have to do is you have to take the subtraction of them. Okay, if I'm comparing, let's say, 10 decibels to 40 decibels. 40 decibels. What you do is you subtract them. So it's going to be 40 minus 10. I'm not really going to care about this. What I'm going to care about is the front numbers. Get rid of those last two. And it's 3, right? So what happens is it's going to be 30. It's really 10 to the third times louder, which is 1, 2, 3. So 1,000 times louder. So I was comparing something that's 10 decibels versus 40 decibels. 40 decibels would be 1,000 times greater. What you do once again is you subtract them, and that number in the ones place is going to be how many zeros you add, and that's how many times greater. So how many times louder is 50 to 40? Well, the difference is 10, which means I'm really focusing on that 1. So it would be 10 to the first, which would mean 10 times greater. How many times louder is 60 decibels? Sorry. How many times is 60 decibels? Well, it is 10,000 times. Let's try to do this math. So it's 60 minus 20. So we get that 40, which remember we don't care about that last thing. So it's 4 is our exponent. So it's 10 to the fourth, which translates to 1 with 4 zeros. So it's 10,000 times greater. All right, wave interference comes into a big part with music, okay? And so the rest of this focus will really be on music. And what you're trying to do is you have different waves. And you're trying to make it either constructive or destructive, okay? Remember, constructive is when you're in phase with each other and it goes larger, okay? So you increase your amplitude. And then when you have out of phase, what happens is that they are destructive and they totally subtract one another. And what you do is when you get these up and downs and they overlap in unique ways, you get what we call as beats when they cancel each other out in different ways. So like, and not perfectly where it's perfectly either constructive or destructive. So let's show you where this wave interference is, where the waves don't perfectly overlap one way or the other. Okay, so first off, this is constructively. Okay, why? Because we've got this and we've got this wave and they come together and they get a bigger wave. That is constructive. This is destructive because we have our two waves. Here's our first wave. Here's our second wave. And they are perfectly out of phase. So what you end up with is a result of them canceling each other out perfectly. But this is more of what we get in real life. We don't have these perfect waves where they're perfectly in sync or out of sync with each other. So you get these patterns of constructive, destructive, constructive, destructive. So where they overlap, so I'm going to focus on the first one, where they overlap, which is right here and here, you get something that's additive, so it's constructive. If you look at this guy is near its trough. This guy is still in its crest, so where we've got is destructive. Notice that this guy is smaller and they get smaller. Okay, so then we've got constructive where they overlap here, but they're going in the same phase. So that would be constructive where they get bigger. And notice you go constructive, destructive. It's a pattern. Okay, let's look at the second wave on the right. We've got a totally destructive one. So notice we have this wave and we have this other wave, and the resulting wave is smaller than each of those. Then you go to constructive where you've got where they add up and the resulting wave is larger than each of those individual waves. Okay, so once again, it goes destructive, constructive, destructive, constructive. So let's label where the destructive and constructive interference occurs. So we've got one wave and we've got a second wave. When we add them together, this is the resulting wave. So this is actually the only wave that we'd really hear, okay? But what you should notice is that we have some destruction right here because that result is smaller than either of the first two waves are. And we've got some constructive right here because the resulting wave is larger than each of the individual ones. Okay, and then on the bottom, circle the louder sections and star the quieter sections. So the louder is where it's going to get amplified, so it's louder here, and this would be where it's destructive, where they cancel each other out. Okay. So how does this apply to music? The other one where they're out of sync, in sync, out of sync, or constructive, destructive. That's what we call beats. That's where you get those beats. It's whoa, 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 whoa. It's kind of it's a cool, unique sound. But what we also want to do is we want to make our musical instruments, and how can you change the sound that those musical instruments produce? Okay, there's many ways. First off, you have to understand that there are different types of instruments, and each instrument will be using a similar philosophy, but they do it in a different way to change their sounds in a similar manner. So you've got the string, you've got wind, you have percussion, you have etc. Okay, so all of them are different. If I look at a violin versus a cello, both are string instruments, but they sound completely different. So how do I change that? If I have a flute versus a clarinet, how do I make that a little bit different? All right, so one thing is that you can change the length of the string. A longer string is a lower note. A shorter string is a higher note. Okay, so if you make it long, it's going to be lower. If you make it a shorter string, you make it higher. So by putting your fingers in different places, you're making your strings longer or shorter. Another classic example is a harp. If you look at a harp, the very short strings have a very high note. If you look at the long strings, they have a very low note. Okay, what you can also do is change this, the thickness or the gauge of the strings. The larger the size, the lower the notes. This really applies if you know violin or any of the string instruments. The thicker the string, the lower the note you're producing. Another way you can do it is make it a larger sound board or sound box, so larger resonating chamber. This is the difference between you look at a little violin versus a big cello. Okay, that's that sound board. It is getting bigger, so it is making a louder noise. So a violin will not be as loud as a cello. And then you also can change the length of the air column. So if you make it a longer column, you make it a lower note. Make sure you understand that if it's longer, it's going to be lower. If it's shorter, it's going to be higher. Think of a big elephant, it's larger, it's going to have that lower tone. If you think of a little mouse, tiny little thing, it's got a very high pitched noise, high note. Okay, so I kind of translate it to little animals and big animals, even though it really doesn't have much to do with that stuff. But all right, so let's label each side of the harp as a high pitched or a low pitched. Remember, high pitched will be a very small string and low pitch will be a long string. So you've got your high pitch over on this side and you have your low pitch on this side. All right, hopefully you have a basic understanding of instruments, beats, and various ways that we can measure our or change our sound waves. Have a great day.